All right. Now the next problem. Let's look at the next problem. And I used to assign this for homework quite a bit, and it was always kind of a disaster. So I like to cover it. It's number 44 on the same page. From data on the first 19 modern Olympic summer games, the mean for the winning distances in the men's long jump equals 308 inches. The median equals 310 inches. And the standard deviation equals 19 inches. What do these three numbers tell you about the original data? Well, let me put those numbers up there. Find my eraser, which is a dish towel. All right, so the mean was 310 inches, and median was 308 inches, and the standard deviation was 19 inches. Well, what do you think? The mean and standard deviation, are they close? 308 to 310, I would say that's very close. These are very close together. You know, these are kind of large numbers. So that tells me there's really little distortion in the data. It's pretty well balanced. So 19 Olympics, half of them were below 308 inches and half were above 308 inches, roughly speaking. So now it's a little I got a little extra knowledge here that I wouldn't expect students to know. There's I got to digress here for a moment. In the 1968 Olympics, they were held in Mexico City. At the time of those Olympics, the world record in the long jump was 27 feet and 4 inches. 27 feet 4 inches was the world record in the long jump in 1968. Well, one of our athletes, Bob Beamon, was getting ready for his third jump. You get three jumps in the Olympics, in track and field competitions apparently, for the long jump. And Beamon took off down the track and he uncorked the jump for the ages. Beamon jumped 29 feet 2 inches. He broke the world record by almost 2 feet. Unbelievable. And I imagine people didn't believe it when he did it, but they measured extremely carefully. They even looked at the video, I'm sure, and it was a legitimate jump. He jumped right off the board. Wind was not unusual. He just somehow really nailed it. 29 feet 2 inches. So I'm a little surprised that the mean and median are this close because of this one outlier, this one anomaly in the records. So probably tells me that one of the earliest jumps was in the modern Olympics was very short, and I believe it was. Well, anyway, because the modern Olympics started in 1896, and there really were no track and field athletes back then. They're just volunteers who came over and jumped, and so probably the early jumps were so short and Bob Beamon's was so long it sort of balanced out. All right. Well, I wouldn't expect you to know about Beamon's jump. Incidentally, this record has been broken. It was eventually broken. It took about 30 years. I think Carl Lewis may have broken it, but not by much. Not by much. No one has yet to jump 30 feet in the long jump. All right. Well, let's get back to the problem. What can we say about these numbers? What can you say? Well, we talked about mean and median, so we're saying, well, they look like they're very close, so we don't expect there's a large distortion at one end or the other. I think that would be a pretty good conclusion. What can you do with that standard deviation of 19? Well, remember the empirical rule says that 95% of the data lives between, approximately 95%, exists between 2 standard deviations below the mean and 2 standard deviations above the mean. So let's do that. Let's look at that. If I take 308 and subtract 2 times 19, I get 270 inches, which is I think 22.5 feet. And 22.5 feet sounds, I think that's pretty close to what they jumped in 1896. I'd have to look it up, but I think that's probably fairly close. If I add 2 standard deviations, I get 38,346 inches. All right, so we predict, or estimate. Let me use the word estimate. We estimate 95% of the jumps were within the, let's see, 270 to 346 inch range. All right, so that's a little piece of information we can kind of guess out of this using the standard deviation and the empirical rule. About 95% those jumps fell between 22.5 feet and whatever that is. Okay, I think it's 28 feet something. And actually, I think that's actually true, because 95% of 19 is about 18. So about 18 of the 19 jumps fell within that range. And there probably was one jump outside that range. Matter of fact, there was. It was Bob Beatman's jump was actually more than 2 standard deviations compared to those numbers. All right, so anyway, that's kind of a little analysis, and I've pondered often in this course, how can I teach analytical thinking? And I think if I knew that answer, I would be rich, because I don't know if anybody can teach analytical thinking. All we can do, I think, is to give you examples. Hopefully you learn from our examples and become more creative. And it's a big reason you take math in college, is to get better at analytical thinking. You get that way by practice. And so analytical thinking is being creative, taking information, and really working with it. So I wish I could teach that directly. I think, because would you have thought of this part of the analysis, to look at the standard deviation in that way? I don't know, but that's what I hope to teach somewhat in this course. So it's not a how-to thing, because I can't tell you how to think analytically. All I can do is hopefully you'll learn enough by example. All right, I think that might do it for the examples I go over in this chapter. So let me just oh yeah, let's look at problem 51, page 168, number 51. During the baseball strike of 1994, reports revealed that the mean salary of the players was approximately $1,200,000, and the median salary was $500,000. What do these numbers tell you about the distribution of salaries for baseball players? Well, this is an examination of mean and median again. The median is $500,000 in 1994, meant that half the players earned $500,000 or less. Half the players earned $500,000 or more. Now, here's the median at $500,000. There's a mean at $1.2 million. What explains that? Well, half the players can only earn from 0 to 500, but the sky is the limit on the right side. You know, there were players earning multiple millions of dollars even back in 1994. And so these figures out here would create a distortion in the mean, not so much the median. It would create a larger distortion in the mean. So that would be a pretty good explanation why those numbers are so different. Okay. I think that will do it for chapter 4. So I will see you in chapter 5.